Hi, my name is Thomas Schmidt of the Media Informatics group of the University of Regensburg in Germany, and I present today a short paper titled Exploring Multimodal Sentiment Analysis in Plays, a case study for a theater recording of Emilia Galotti. My co-author is my supervisor here in Regensburg, Christian Wolff. Emotions and sentiment are, of course, an important aspect of any form of literary text and especially of plays. They drive the plot, they evoke reactions by the reader and viewer, and much more. Indeed, in digital humanities, researchers are exploring computational methods of sentiment and emotion analysis, for example, to explore group-based distributions, progressions throughout a play, or evaluate approaches against annotated material. However, as is often the case, current research is rather focused on the text of a play and thus performs textual sentiment analysis. Now, for our small case study that we present today, we wanted to explore other media channels than text, and we will focus on the concept of sentiment, which can also be called valence in our setting, meaning if an expression is rather positive, negative, or neutral. Our main argument is that most plays are not intended to be just read by people, but to be also performed on stage. Our assumption is that the inclusion of a performance and other channels beside text can improve sentiment analysis, since we can use cues like facial expressions, like voice, and so on, and we might avoid problems on text level like the historical language, the poetic language, and so on. Now we will see throughout this presentation if this assumption actually holds true or not in our setting. As case study, we use a recording of a 2002 theater performance of the play Emilia Galotti by Lessing, which was performed at the Wiener Burgtheater. It's a canonical play for German literary studies, and we basically extract the text, we extract the audio, the video, and then we perform sentiment analysis with recommended ready-to-use solutions, as we'll see in the coming slides. Our first step was, however, to actually get the real text of the performance, which differs quite substantially from the original source material. We did this primarily via speech-to-text. We used Google Cloud speech-to-text for this. This produces single text units of the spoken content based on breaks during the talk. We also received the corresponding timestamps for all these specific units, and then actually looked at the text and realized that the output is rather mediocre, so we needed to manually post-correct the output, add some missing text, and so on. And overall, we had finally 672 text units that we regarded as our material. Now for the other channels, we used the timestamps that we also received to extract the audio snippets and also the video snippets for the specific units. For the video channel, since we perform image-based sentiment analysis, we also extracted 1 frame per second for each of these video snippets, and these images we will later use for facial sentiment prediction. On the textual level, we performed lexicon-based sentiment analysis, which works with predefined sentiment lexicons, which are lists of words annotated with sentiment information. We use a basic calculation process to deem a text unit negative, neutral, or positive. We sum up the values for the positive words in the text, and we subtract the values for the negative words. And in our setting, we use CentiWS, a famous German lexicon, and we also applied some general recommended pre-processing steps to improve this process. For the audio sentiment analysis, we used the tool Vocaturi. It's an emotion recognition tool for spoken language, based on machine learning neural networks. It is recommended in some research as the best free software for sentiment analysis of spoken language, and we basically use each of the over 600 text units or audio units as input for Vocaturi and receive numerical values in a range from 0 to 1 for 5 emotion categories. Now to map this on our 3 classes for sentiment, we sum up the negative values, the emotions connoted negatively, and compare them to the neutral value and the value for the positive class. and then we basically assign the maximum as the actual sentiment class for our 3 classes. For the facial sentiment analysis, we use the Affectiva Emotion SDK. It's basically also a tool based on machine learning, trained on a large training database with over 6 million faces to perform facial emotion recognition. Entering an image, we receive valence sentiment values that can be positive or negative, and we simply create a sum for all images of the video snippets, so 1 frame per second, to calculate the final valence value, which can again be negative, positive, or neutral. Now, to evaluate the approaches, we needed to annotate our corpus. For this, 3 annotators annotated each of the 672 video snippets, considering the sentiment classes. The annotators were presented with the video and the text via a table for the annotation, so they had access to all modalities, so to speak. And what we found is that the agreement among annotators is rather low. They agree on average on around half of these units. Now, this low agreement is in line with similar research on this text sort and shows the problems of this kind of subjective and complex literary material. However, one assumption we also had is that the presentation of this video channel might improve agreement. But as you can see, this has been shown to be wrong in our case with kappa values of 0.2, which is very, very low. Nevertheless, the annotated corpus can also be found online if you are interested in material like this. For some context, this is the distribution of the final annotation and our gold standard. Around 40% of the final units are neutral, 40% are negative, and only 20% are positive. Now first we take a look at the distribution of prediction classes for each modality. For text, almost half of the classifications are negative, while for the audio channel, this increases to 63%. For audio, however, speeches are rarely classified as neutral. On the contrast, for the image analysis, we identify most speeches as neutral, actually a lot of speeches, which is obviously points to a problem, which I will get to in a couple of slides. Nevertheless, it is clear that all channels seem to behave rather differently. However, looking at the probably most important thing, the performance of these approaches, the accuracies of all approaches are quite similarly low and rather disappointing, around 45%, which is just slightly above the majority baseline. So overall, we regard our experiment as negative result in this setting and specifically with these tools. Now, what went wrong? Looking at the problems for text, we identified the usual well-known problems in this setting, and for this kind of text sort, like dealing with irony, sarcasm, the historical language, metaphors, and so on. The approach also has problems with very short speeches when not detecting any sentiment-bearing word. And for the audio, one problem might be that our heuristic matching the emotion output to the sentiment classes was a bit problematic, and we also identified some biases in the sense that, for example, male voices tend to be classified negative and female voices as rather positive. Just to give you an example for the image analysis, in the upper field you see an image of a speech correctly predicted as negative, while you see below a speech falsely predicted as positive. We identified that the model has problems dealing with grimaces and similar more complex facial expressions, as you can see here. Now, the main problem of the image-based analysis are, however, images like this, or also simply when actors do not look directly into the camera. The model then has a problem identifying the face correctly, which is a first step for the actual sentiment prediction. This makes sense when looking at the image databases these models are trained on, which are indeed based largely on faces looking directly into the camera. And this is also the reason, looking at another example, why an image like this works very well and is predicted correctly as negative, and an image like this is predicted as neutral since no face is detected. If we did not identify any face, the class neutral is assigned. Thus, this huge proportion of neutral classes for this method. So what's next for us? Of course, we use non-optimized, ready-to-use solutions. While they are recommended, they have been proven to be not good in our setting, and we want to adapt existing models to our use case with more annotations. One basic problem that we encountered is that we did not include a mix class, which is of course important for longer speeches, switching between polarities. And also the applied image-based approach is phase-focused, neglecting maybe other important aspects like body movement. Of course, we did also not apply any complex fusing method of the approaches, which is actually our main goal, to employ real multimodal sentiment analysis. So nevertheless, I hope you had fun with this talk, and I'm looking forward to your questions.